And hello, everyone.
Hello. Awesome. Thank you guys for coming in today. Welcome to the Global AI Festival. We are starting off with I do want to say one of the best cities in the world, New York City. Yep.
If you would like to put in the chat hello from where you're joining us from. New York is very encouraged, but everywhere is encouraged as we are unifying and promoting diversity in AI. So why don't you go ahead and say hi in the chat, and Terragor is going to tell you a little about AI.
Yep. So yeah, so here at the Global AI, we're starting for New York, and what we're doing here is building a community of data enthusiasts, AI enthusiasts, trying to get people all over the world to come together and learn from each other, learn what's happening with AI, and how we can leverage AI to help us in the future. And yep, so over the next few months, we will be having conferences all around the world. And we will be using a platform called GatherTown, where we can come together and network. And Hope, do you want to give a quick intro to how GatherTown works before we get started?
So GatherTown will be our networking platform for the networking hour at 3 o'clock, and I will give a little tutorial for that after all of the presentations. But it's kind of just a fun, very unique gaming type networking platform that we hope you'll all join for at the end. We hope that you can all join for that part, because that's going to be a lot of fun. There's like a gaming room and everything, but we're going to specifically gather in the DJ room, and I will show you how to navigate that at the end here. Terracor, did you want to tell them about City.AI?
Yeah, so we started off a few years ago, especially with the whole COVID, it kind of slowed down, but we're trying to get back into speed, get back into action, and learn from each other. So we do have a full afternoon full of great speakers. And one of our first speaker who is giving the keynote, he is Brian Knaus from Project Owl. Brian, are you here?
Hello.
Awesome. So Brian, feel free to share your screen and give yourself a little intro, and you can get started.
All right, let me find a good position here. I got some, it's sunny out today, so I have a glare, but it's a pleasure to be here. Again, thank you, Terracor. Brian, I'm Brian Knaus. I live in New York City. I've been hopping around the meetup AI technology community in New York for a very long time. Unfortunately, that hasn't really been available over the last 2 years, but it's nice to see events like this, whether they're just virtual or starting to see, things coming together again in person. I really enjoy that. It's an environment where I've made a lot of friends and built great connections, including some folks here on this call. So I have I suppose a deck we will run through when I share my screen. All right, can we see this?
Yep.
Yes, we can.
Yes.
This is the wrong year I put on here, but hold on, let me move my Zoom thing. Okay, cool. So I don't have the jersey in front of me, unfortunately. We'll get to it in a couple slides, but I've titled this AI. Is AI the answer? There's a lot of discussion today, especially if you spend time in Silicon Valley communities, tech communities. There's a lot of talk about AI, and AI isn't one specific thing, but it's really a consortium of technologies, ideas, perspectives and strategies on how to leverage technology and what it can empower for us. And AI means different things to different people, right? To some people, AI is that thing from the movie Terminator that's going to end us all. To other people, AI are deep learning convolutional neural nets, right? And that have no moving element, robotic element to them. So it's AI is not so much a specific thing, but there's a consortium of technologies and capabilities that it empowers. We'll talk a little bit about today. So again, a little more background of myself. I just love building technology that makes an impact. From about 2014, when I really moved to New York, to 2018-ish, I was just going to hackathons all over the place, technology competitions. I'd imagine most people here know what a hackathon is, but if you don't, it takes two of my favorite things together in the world, and that's competition. You know, I love sports, love watching soccer, basketball, football, and building stuff, being a nerd, right? And puts those two together. In 2018, I was very fortunate to have, with a team of folks, including TerraCore, to have won a competition called the IBM Call for Code, which was a global technology competition that asked companies to, or I should say people and groups, to come up with ways to help communities prepare for, deal with, and recover from natural disasters. One of those gentlemen was TerraCore Rahman, who you met just a moment ago. And we named our idea Project Owl. We ended up winning the competition, and it's launched our company, and that's where I've been working ever since. So what do we do at Project Owl? We build simple wireless technology connecting the people, places, and things you care about most. And I'm not going to talk too much about Project Owl here today, but just to give you a sense of my background. So we build hardware devices that acquire data through sensors or people accessing them, you know, with like a phone. And they share that data in something like a mesh network in a lot of locations. And this gives us access to data sets to perform other types of analytics, visualization, and ultimately down the road, once we scale that, more machine learning. So the inspiration for this discussion, you know, there are a lot of sources, but if anyone here is thinking like, okay, I want to wrap my head around, I've got three different things that might be worthwhile checking out. And each of them correspond to three different skill levels in the space. So I think there's something here for everyone. If the first one I'd recommend is it's a long form article. So it probably take you, I don't know, 15, 20 minutes to read. It's called The AI Revolution by Tim Urban. He is a fantastic writer, and some of the graphics throughout this article are really great and provide a little comic relief. You'll see a couple of them later in this slide deck. The next one is AI is the New Electricity by Andrew Ng. Andrew Ng is a widely respected researcher, computer scientist, and I think is generally regarded as one of the pioneers of the last few decades in AI, generally speaking, machine learning. He was the chief scientist at Baidu for some time, and more recently, I think he started TerraCore. He started a couple AI educational companies as well as some other stuff more recently.
Yeah.
And then the last one is a book called Superintelligence by Nick Bostrom. It's very interesting. It's extremely dense. So if you're not into AI or don't have background, it might be more of a challenging read. It's a couple hundred pages that reads kind of like a research paper. So for those of you who like to go deep into the science and stuff, it has some quite interesting perspectives that I highly encourage checking out. And I have links to all of these if anybody's interested. So I know we're not in person. This is easier to do when I'm standing in front of people, but some of you on this call may know who this is. I am from Philadelphia. So again, I mentioned sports fan. This is probably the greatest Philadelphia 76er who ever played the game. His name is Allen Iverson. Many people called him AI. And interestingly, he had another nickname he went by that he was called The Answer. So AI, the answer. So the question is, as we're going into this, is AI actually the answer? And again, to go deeper, I think it's important to also, again, clarify a little bit more of what exactly is AI, because especially in technology circles, AI is not a specific thing. So when somebody says AI, you really have to drill down to what they mean by that, right? To what I would dub as like an outsider, AI is those Terminator robots. But to an insider, AI is pattern recognition on data sets, right? And those sound like two very different things, but they both kind of conform under this same bubble. So why do I have a cornfield here, by the way? You may be asking. I thought this was an appropriate kind of message from, I come from Eastern Pennsylvania. There's a lot of cornfields here, so it's near and dear to my heart. But also, I think this image brings together a unique perspective on the combination of artificial and organic. I would consider corn, generally speaking, pretty organic. We didn't invent corn. I don't know when it started growing on Earth, but I suspect it was long before we realized how to harvest it. You just kind of plant some seeds and this thing grows with some water and some sun, and it's actually quite a tasty food, and you can do all sorts of great recipes with it. Lately, my favorite is elote, but I digress. But in this photo, the key here is that's the organic. The mathematical precision of the way this is planted, that is not. So these are in perfectly straight lines. And very rigid geometry like this is not something that happens organically on Earth, or generally speaking throughout space, right? Nature is messy. You don't see mathematically rigid shapes and lines like this, things that conform to almost unnecessary precision in a way. So too in AI, it seems that artificial intelligence is a hybrid of our artificial world, our machines, with the organic, our intellect that we have somehow evolved into. Okay. So my generic description is artificial is something that is made or produced by humans rather than occurring naturally. We call this technology. And intelligence is the ability to acquire and apply knowledge and skills, or in other words, our brain. So our compiled definition may be technology that resembles the capabilities afforded by our brains. So, those of you who are new to AI, those who are quite experienced, sometimes we may ask ourselves, like, why AI? What does this really do for us, right? And some people are scared of it. Some people are scared of technology and where it's going. I think a lot of discussions say around Facebook, the algorithms, content, are they manipulating us, types of things. And even those scared of, the robotics AIs, right? Like, have any of you seen Boston Dynamics, some of their videos? On one hand, I think those robots doing backflips are some of the coolest things I've ever seen. But on the other hand, I have this nagging feeling like, is this a sign of the end times? So why AI? I mean, for me as a technologist, humans have always been adventurers and explorers. So if given the question of should we go explore the new world or see if there is a new world somewhere, a lot of folks will say, why not? Right? This is a really fascinating environment. And I think for all of us, we're living in exceptional times where there's so much exciting activity in science and technology that's happening at a more rapid pace than ever before in human civilization. And that's fascinating to me. So why not explore this further? I thought a nice way to think about the advent of AI is with a programming analogy. So it's a simple if statement, and it goes like this. Assuming that there's really any continuing ongoing human technological process, and also assuming that we don't go extinct, in the relative short term, we will continue to compound intelligence over time. And to be clear, I don't believe our biological human intellect is expanding. I'm referring more to our technological digital intellect. The intellect exhibited by the machines we are creating is compounding exponentially over time. And if these rather mundane assumptions hold, then it's probable that we will develop a technology called a digital superintelligence, Nick Bostrom, or an intellect more capable than all the human beings in the world combined. And we want this because, and again, why? We want this because this digital intelligence can help us accomplish humankind's goals in mathematics, science, exploration, medicine, energy, finance, war. But again, a digital superintelligence, wow, that's some cool words. But before you get too excited, we should be careful, right? I've only been around a short time, but knowing what I know about humanity, if we built a machine smarter and more capable than all of us, this sounds like it could go very poorly, right? Humans make mistakes. So let's think about the timeline of this development to get a sense of our rate of progress. This isn't the first time right now that folks have been excited about artificial intelligence. In fact, another way to say this isn't the first hype cycle of artificial intelligence. And we'll look at that in a bit more in a moment. And these hype cycles have waxed and waned through the ebbs and flows of interest and investment over really the last century or so. As to when AI officially began as an endeavor, it really depends on our murky definition of AI and how you specifically want to address that vague nomenclature again. If AI is a technology that resembles the capability of the brain, it was the abacus tool, that original calculator, some semblance of an AI in a way. Certainly didn't have a digital element to it, but technology that expanded upon the intellect that we have. What I do think we can agree on is that a modern understanding of AI rose to prominence as a topic of research and academic interest in the early to mid 1900s with the advent of machine computation. And while many debate the efficacy of the Turing test as an actual test of machine intellect, or maybe more appropriately, one of human stupidity, it marks a seminal moment for the belief that one day machines may actually be smarter than us. And this period culminated with a famous conference of researchers at Dartmouth College in 1956, where it was proclaimed that every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it. This excitement waned with one of several AI winters and increased again with the development of expert systems, such as Deep Blue, which defeated the world chess champion Garry Kasparov in '97. AI has regained momentum in recent years and right now is driving market capitalization for some of the world's largest companies, Google, Facebook, and Baidu. So while we pose the question, is AI the answer? We pose this because this isn't the first time AI has been at peak hype cycle or thought of as the answer. And so the question is this time really is this it? In 1958, some prominent researchers were saying within 10 years, a supercomputer will be the world's chess champion. And of course, it took nearly 4 times as long as expected. This overzealous ambition has repeated time and time again in the industry. Most recently, Ray Kurzweil said, even just in 2018, that the technological singularity will occur in 2045. And for those wondering, what is the technological singularity? It's loosely defined as the time when technology is so far superior to humans at every potential task we would want to accomplish that there's nothing left for us to do. Maybe a little optimistic or pessimistic. There have been problems developing AI. And these have occurred for many plausible reasons. One I find interesting, though I don't know the scientific merits of this claim, is that the human brain is the most complex object in the universe. I think this perspective is a little self-righteous, but it has been echoed by several prominent scientists. And I do find it fascinating that despite the wide availability of human brains to ponder this, we do seem to really not have a good understanding of how it works. So it seems trying to recreate something that we don't understand would lead us to these hype cycles and failures that we've continued to see over time. And this is identified in something called Morvx Paradox. And that, if you think about it, AI does everything requiring thinking, like multiplying two 20-digit numbers together without fail over and over and over again instantaneously, but fails at everything we do without thinking. In fact, up until recently, it's been very hard for a computer to look at two photos, one of a cat and one of a dog, and to say, this is a dog. And we don't think about that. We just do it. Another example of this challenge is, when I was in college, I used to love drinking this vitamin water. First of all, it was the best flavor, kiwi strawberry. But second, I was looking for a little more focus, and this was the focus vitamin water. So I thought, if I can drink this, I'll be good and I'll succeed in my tests. Needless to say, it didn't work, but I was always fascinated by what was on the label. And I'm just going to go ahead and read. A recent study found that it doesn't matter what order the letters of a word are in. The only important thing is that the first and last letters are in the correct position. Unfortunately, that's not the case with everything in life. Sometimes the in-between stuff matters. Now, I won't read the whole thing, but all the letters are screwed up here. You can see that. And at face value, it kind of looks like this would be impossible to read. But when you read it, your brain just kind of figures it out. This is the type of thing that humans can do without thinking, but until recently for computers, supremely difficult to figure out. This is one of these Gartner hype cycles. So if you haven't seen these before, generally what this curve is showing you is as an innovation, a new technology is triggered, it goes through these periods of high interest, inflated expectations. And then what they call the trough of disillusionment, the realization that, wait, this needs a lot more work. And it's not as good as we thought it was going to be. And over time, as technologies develop, they plateau into productivity. They become real, right? And it's not some fantastical thing like they are up here, but they do have application in society. And I do find that in 2018, at least, that some of the most hyped technologies are all things I would consider kind of the AI stuff. I mean, even other ones, brain computer interface, mobile robots, right? Like pretty much you could almost lump to a degree pretty much everything on this curve into AI. So we might be at peak hype again for AI. And the latest expectations is that superhuman artificial intelligence will occur within the first third of the next century. And Nick Bostrom said that in 97. And then 20 years later, he said, actually, we have no idea. So, and also detonation makes it sound terrible, but there's essentially this thought that if AI continues compounding exponentially and their capabilities continue to compound exponentially, that there will be this AI explosion where computers start to become substantially more capable than us. And that progress is rapidly accelerating. So we ask, is this time different? Is AI the answer to all of our problems this time? There are two reasons I suspect this time may be different. One is the deluge of data we are living in. And certainly it's all the stuff we post online, the Facebooks, the Twitters, but even in the way companies and enterprise organizations categorize that data, frame that data. You'll notice in this 2018 Internet Trends slide that the amount of data available or being created is growing exponentially, as well as the amount that's being structured. And that's critically important for computers to be able to digest and use it. If you remember that vitamin water, that was some unstructured data that's very hard to read, but if you can just structure it the right way, a computer can leverage that. And the second thing that I think leads us to this time is different is the explosion of artificial intelligence hardware, the realization that GPUs are actually, weirdly enough, originally created for like video games, are the best silicon we have available until recently, with some very specialized ASICs, application-specific integrated circuits, FPGAs, as well as tensor processing units Google's been working on. But there's really been an explosion of AI-specific convolutional neural net, deep learning specific hardware. One way to think about this more practically is if technology continues exploding, the amount of teraflops, in other words, or flops, calculations per second, floating point operations per second, per $1,000 has been exponentially increasing. And in the year 2000, what was available to us is about one insect brain of a computer, but you can see the trend line here, right? And that something very interesting is going to happen in our lifetimes with the digital technology and artificial intelligence available to us. This is from that Tim Urban article, but another way to think about it is if there is an AI intelligence explosion, it seems stupid. The delta between the dumbest human in society, and I'm sure maybe some of us could imagine who that is. We may all have different opinions. And the delta between that and the smartest human in society is relatively small on the grand scale of intellect, right? So, but the belief is once our digital technology reaches the dumbest human, it's not just going to stop there. It's going to continue to accelerate and blow past us very quickly. And this has happened for, among other reasons, because the cost of building technology has dropped substantially by orders of magnitude over the years. In other words, synonymous with the cost of launching a startup. I realize I'm going over time here, so let me just see how many more I got. Okay, so we're going to do this slide, and then I'm just going to quickly go in. So exponential growth. You hear that term a lot. Exponential growth is interesting because it's something maybe we understand mathematically, but we don't understand or have a real good grasp intuitively. And so what I mean by that is, like, imagine you got a pond in your backyard, a bunch of frogs on it, and some lily pads start growing. Now, these lily pads double in number every day. And if we have one assumption here that it's going to take us 30 days for the pond to be fully covered in lily pads, on what day is only half the pond covered? And the answer is on the very last day before day 30. So it takes 29 days in an exponential growth scenario to cover half the pond and one more day to finish it. That's the power of exponential functions. So is AI the answer? I'm not in a position to say that. Unfortunately, Allen Iverson was not for the Sixers. They made it to a championship. They never won one. And now they have all sorts of other problems. I think AI has the power to solve a lot of issues in society. I think some of the applications of it are phenomenal. Self-driving cars is a big one today. I don't think it will solve all of our human problems we see going on around us, but that we can leverage AI to help bring us to a better future than we are at today, with applications in medicine, finance, farming, agriculture, hopefully even solving our politics, but I'm not optimistic. In any case, I appreciate the opportunity to be here. I thank you all for joining today. I would take questions, but I'm wondering if I'm going to make the organizers angry if I take any more time. So thank you.
Well, yeah, so thank you, Brian. That was actually great and very entertaining as well, too. I'm a Allen Iverson fan, so yeah. So to answer your question, so Brian, you have your contact information on Twitter, and you will share those slides as well too, right? So you guys can have.
Yeah, if you want me to just email it with you.
Yeah, that would be great.
Yeah. Yeah, and for those in the chat, the rest of my slides weren't that interesting, I promise. But the main point was you can access a lot of this stuff on IBM Cloud, Google Cloud, Microsoft Azure. There's a lot of tools available to you, conversational assistance, machine learning, pattern recognition, all sorts of goodies. You don't even have to know how to code to use some of these cool things like visual recognition. So I encourage you to check them out. But we can follow up more in email. In any case, thank you. I appreciate the time and the opportunity. It's a pleasure to be here. Thanks, TerraCore. Back to you, man.
That's actually a great segue to our next talk about using you don't have to code. So the next talk I'm very excited for. It's a reinforcement learning, and this is something that I just recently dived into. I'm trying to learn that as well. And without giving any more secrets out, I'll let the next speaker talk. This is Dr. Sahiki Jenk. I will be sharing the slides once I have it open.
Hello, everyone. I'm going to take over from here while TerraCore is bringing up the slides. I'm really excited to be here. I'm sorry that I won't be able to share my video because I don't have a really good internet connection, and I want to make sure that everybody can hear me. But I have lots of materials you can find in TerraCore. Actually, the PowerPoint also uploaded. So if you can give it a try, it has some of the videos. But if it is taking too long, I will continue with the PDF.
Yeah, I'm having trouble opening the slides.
Okay, no worries.
Yeah, sorry about that.
Yeah, so the only difference between the PDF and slides are I had several videos, but almost all the videos that I had used here, you can find it if you search for AWS DeepRacer. And I'm a, excuse me, I'm a principal applied scientist as Amazon AI, and it's a joint talk with my partner in crime, Sunil Malia. What I wanted to do today was, it's kind of, I think, in sequence to what Brian was talking about, how we can use robotics and other sensors, automated systems, and have them improve with AI. And this is a very good way, in my opinion, and also continuing on that AWS DeepRacer is also available. It's open source, and you can get started on this, what I'm going to share today, almost immediately, with lots of resources available, not only from Amazon, but enthusiasts and community members across all over the world. They had shared lots of different things that they had done with DeepRacer. Next chart. I wanted to get started first with, when I talk about AWS DeepRacer, not everyone is as familiar. And so I wanted to get started a little bit about how we decided on this path. In 2018, we were seeing that reinforcement, especially deep reinforcement learning, is a growing field in the AI domain. But we were also realizing that there were a lot of unknowns, and there were a lot of educational resources, but not much practical resources that the ML practitioners can go learn about deep reinforcement learning, test their skills, and then take this skill set back to work and improve their own businesses. So we started thinking about how can we do this in a fun and exciting way, but at the same time teach people about deep reinforcement learning and enable not only our software developers, but others in the community to get hands-on with deep reinforcement learning. So we started building this toy car, and I'm going to talk a little bit about how in academia we will start with toy problems. So we decided to start with toy cars. And we previewed what we called deep reinforcement learning with AWS Deep Racer. And Deep Racer is a robot car. And this robot car is actually a 1/18 scale car. And we previewed this at reInvent and MGM. It was a big hit. Everybody was so excited about having to have hands-on experience. In 2019, we launched this product, and we had, by the end of the year, we had 30,000 participants training either models, being part of the Deep Racer League, hosting summits across multiple countries, hundreds of in-person races. So what was really exciting about Deep Racer was that it wasn't only that you would go and train your models in a simulation environment using your sensor data, but we enabled people also to download their neural network models into the car. Literally, you just put it on a USB drive and you stick it into the car, and voila, that you have a neural network that is doing autonomous car racing on this 1/18 scale. It was super exciting, and in 2022, we grew to 50K participants. And in doing so, we also learned from our community partners that people are interested in putting more sensors into the car. So what we did in 2020 is we enabled that people to put add-on sensors such as a LiDAR, additional cameras, and then enable obstacle avoidance and or multi-car racing. So really took it to the next level. But at the same time, what happened was because of some of the precautionary standards around COVID, we started what we call underground racing. And if you have a large basement, we have great ideas on how you can decorate your basement. So I provided a link here, and if you search for Deep Racer Underground, you will see that some of our community members started putting Deep Racer tracks and running models on others' behalf, and it really helped us grow the community. In 2021, we grew to 80,000 participants in our virtual league. And in addition to these community races that you can host on your basement, and you can always email me if you want to know more about it as well. We partner with other community leaders such as AI Driving Olympics and AI Crowd. And these are nonprofit organizations who help ML researchers to get jumpstart on things that they can methods and ways that they can learn either deep reinforcement learning, deep neural networks, machine learning, and such. So we currently have a NeurIPS competition going on. If you're interested, I provided the link, and you could go actually join and participate in this competition. And depending on your ranking, if you're competitive, such as Brian, you are going to, you can win a Deep Racer car, and or we will be supporting it with AWS credits at the end of the competition. So this is really the progression. And when Tarakur mentioned about this opportunity, I was like, this is great, because we really want to have community take on AWS Deep Racer further and find out different kinds of applications around it. We also open sourced our device code. It is all written in ROS 2. So you're also welcome to go to internet after today's presentation and look for open source code, not only for software development, but also software development on the actual car. Let's go to the next chart and see how we get started. For a long time, my desk looked like on the left. And as you can see that while it's a toy car, it's not necessarily a toy problem. And this is where I want to make the difference, that when we get started, we wanted to go really, really big. But then we really learned that maybe starting with a toy car is actually better because it has more challenges. Most of the mechanical parts aren't Six Sigma, as you would actually see in the industry. Most of the components, the motor, the servos, and the gears and everything, they are actually produced at low cost, meaning that they're not restricted to Six Sigma like quality metrics, that from one car to next car things will differ. And we thought this is a great opportunity for AI to shine, partly because you might have seen a lot of descriptions about it is really difficult to scale to AI. You get it working on one machine and it's really difficult to take it to another machine. And this toy car turned out to be not a toy problem like we would have in academia. So it was early on, we took on the opportunity to say that we're going to develop the hardware and software at the same time. We're not going to spend all our time working on the software and realize at the end that our software or our deep learning neural network model doesn't transfer into our cars. So you will see in the next chart, I actually included some videos, but you could find these videos in the next chart, that we started out saying that let's have a prototype of a car. So you're actually seeing the prototypes that we have, which is apparent from the duct tapes that you're seeing. One of the most important arsenals, not only to tape the sensors and make sure that you can find the right camera angle, but also we use duct tape to build kind of roads and paths that the car can take on, which are really arbitrary. We started really simple. We said that in the software, let's try to first learn how to go straight, and then we can learn how to turn. So we gradually go between the software and the hardware, and the software and the hardware, and the software and the hardware. And every time we made a change in the software, we went and confirmed that on the hardware, and then we came back. And this kind of constant feedback loop really enabled us, and which I think is something really missing in the robotics community today, that folks are either focused too much on the mechanics or they're focusing too much on the AI, and they're not really marrying the two and creating this continuous cycle of going back and forth. It really enabled us to move forward really fast. Before we know it, we were doing tracks around this bigger track. However, our dreams about drifting had crashed very quickly because we realized that we don't really have the right mechanics to enable it. So let's go to the next chart. So let's go into a little bit of introduction to deep reinforcement learning. I'm not really going to go into the very technical depth of reinforcement learning, but I'll give you an idea about how the car learns how to drive. Reinforcement learning is, in the broader context of AI, it's actually a method that has been developed in the 1950s, and it was developed as a means, can we learn by trial and error? As you can see, it's a very big principle in engineering that you always do trial and error, and you want to make sure your program or your hardware is working, and you go back and forth. So the folks were really thinking about how they can take this and create an optimal control by learning through these trial and errors. And one thing they added to this trial and error is what you hear, the reinforcement part, that they added a reward at which, if the trial that results in a good outcome, then you incentivize your algorithm. This is a good one. You can continue to learn from it. Similar to how in supervised learning, you would label the good data, the outcome that you want to achieve accordingly. So in the reinforcement learning, you're doing this with a reward. So in the 1980s, that modern reinforcement learning came into picture, because then they started saying that how can we marry this learning by trial and error with optimal control? And most of the development there was how can we design better rewards in order to learn, and how can we theoretically also show that the algorithm is going to converge. Then we can also provide some we can also have some theoretical boundaries on how and when we can have these algorithms safely operating in the real world environments. And in 2010s, DeepMind had came up with deep reinforcement learning, where they said, well, previously, all the reinforcement learning methods, or most of them, required first principles, that you really have to go in and design the components of the environment. So in the context of physics, you can think of that if you're designing a car which is learning to drive, that you would like to provide physics associated with Newtonian physics that includes friction, steering, and how that steering and acceleration will result in the distance and velocity that the car is going to travel. However, what was happening was, if you have, for example, cameras, it will be really difficult to create those models unless you're learning on the fly and you're learning from the data. So what deep reinforcement learning did was, can we marry reinforcement learning with deep learning, that we're not actually spending time creating these first principle models, but we can learn the models from the data that we are using to actively learn. So this is also how we differentiate reinforcement learning from supervised and unsupervised. In the supervised learning, that you would have a one-time labeling of the outcomes, and this will create this, then you would learn according to this data set that was created at one time. And you try to create your data set as big as possible, from which that as big or as diverse as possible, from which your machine learning model can learn. The one advantage of the reinforcement learning was that it can actually change its data set, that once it learns from a certain data set, then what it can do is it can continue to say that, well, I didn't actually learn very well on these others. Well, I learned a lot on these, which is the concept of experience replay, which allows the reinforcement learning to actively change its data sets in order to hone in its AI. Let's look at how Deep Racer actually learns how to drive in the next chart. So in the case of autonomous learning, what we are doing is that the car is taking actions on an environment. So these actions are steering, so which angle I'm going to take next, and or which speed I'm going to move forward. And when I say next step, this is the next time step. So in the case of Deep Racer, we actually take steps, our sampling rate at 15 frames per second. And we take actions a little bit slower than that, because you don't want to take action on the data that you observed too far in the past. And then the environment creates rewards. Now you can say that, how does the environment create rewards? This actually happens in simulation, because in the simulation, we know the ground truth. We know things like when the car gets out of the track, when the car is staying on the track. We also know how, for example, we know how long it will take the car to continue a loop. So these are things that we can actually push to the car when it is learning in the simulation, because in a sense, our environment is set in place, and we as the designers know how to create these rewards. And one of the common saying in reinforcement learning practitioners is, be careful what you wish for, you may just get it. And that's basically the idea, that your car is going to be as good as the rewards that you created. If your rewards are not well thought out, your model is not going to learn the right thing to do. Another information that the car gets is state. And state is defined here as the data that the car is getting from its sensors. So in the case of cameras, this would be a 2D image similar to the Atari frames that DeepMind had used. In addition, with the latest model, which uses LiDAR, it can also incorporate, it can also consume vector data. And we also provide you ideas on how you can design your neural networks that they can consume these two different kinds of inputs. And our models kind of go through this circle of feedback, gets these rewards and states. And at first, the actions are really random. And through what we called policy iteration and actor-critic learning, it actually starts with random actions and then looks at the rewards and states. And then in the next batch of learning, it updates its model. In this case, the model is a neural network. Output of it is actions. Input of it is state. And the output of the neural network also is value, which is the cumulative rewards it's going to get. Let's go to the next chart and learn a little bit more about the depth of the models behind it. So, as I mentioned, this is a feedback loop where our car is gathering data from the environment, and then it is calculating what we are actually going to consider is it's going to calculate the gradient estimation of the cumulative reward. So the reward it is going to get, not right now, but the reward it's going to get over the course of an episode corresponding to either car getting out of the track and or car continuing a loop. If I take this cumulative reward away, and if I reward the car for immediate rewards, then we boil our problem into what we call bandit type of problems. So this is the big difference between bandit and reinforcement learning. So you can also think of this is that the car is learning to optimize over a horizon, not just for today. And in that sense, when you're training reinforcement learning using this loop, what you will see is sometimes the algorithm will take some actions that doesn't make sense to you at the moment, but it actually is looking ahead and trying to maintain a cumulative objective or cumulative reward over the course of the horizon that it is going to drive. And then the next step is let's update the policy using the gradient ascent. I'm saying ascent in this case because we're maximizing the rewards. But if your reinforcement learning is actually minimizing or penalizing undesired behavior, then you can actually formulate it as a gradient descent. At the end of the day, you have a neural network that you're constantly updating. You're coming up with new weights based on the experience that the car had gathered. Now you can ask that, well, when does the car decide to go with the neural network and continues with the actions that maximizes the reward? So there is one differentiation also that puts reinforcement learning different from other machine learning methods is what we refer to as explore versus exploit. And what happens is that while we're creating this replay buffer, we design our outputs such that they also come with they come up with actions the car is going to take, but it also comes with probabilities and rewards that we calculate that we would get, which we refer to as values over the course of the horizon. Now, what happens is most of the time we say the algorithm will take the actions that maximizes the reward. But at some times that we deviate from this, which we call an explore mode. And in this explore mode, we take actions that are not maximizing the reward, but our uncertainty in predicting that we're going to maximize the reward is calculated accordingly. And sometimes people use uncertainty, sometimes people use entropy, sometimes people use what we call epsilon greedy, and it's just based on creating a random number to take exploration. So the idea here is that the neural network, when it creates these outputs, it will also provide you some additional information such as entropy, uncertainty, which you can use in this feedback loop to design your next set of experiments to include exploration that may help you learn about a new reward that you learned about a new maximal reward that you haven't learned about. Now, this explore and exploit doesn't really matter. If you have linear models, you're likely to exploit more than explore more. But if you have nonlinear models, which are more difficult to learn, that you may prefer to explore because there may be that one reward that you haven't yet reached, such as a bonus that you will get when you get to the finish line of the loop in a shorter amount of time. So those are the things that, in a nutshell, components of a reinforcement learning that enabled our car to learn autonomously in a simulation environment. Let's go to the next chart and see how we actually go about it in the real world. So what we learned through our experiments is that depending on this linear versus nonlinear, what we learned is that it is agent's neural network is approximating the future cumulative rewards. And what we learned is that there is a relationship between how you design your reward, which is the human component right now is this AI development. But there are currently methods out there that enables you to learn the rewards. Let's say for sake of discussion that this is a problem, autonomous driving, where you know how to create rewards really well. But depending on how you create these rewards, we learned that some neural networks, such as very shallow neural networks, nothing like ResNet, but a couple of layers of convolutional neural networks can learn really well, even though they're consuming image. Some of these reward functions really well. In some other reward functions, they don't do a really good job. Let's go to the next chart and take a quick look at an example. So before I provide the example, I wanted to give you that when I say simple and shallow neural network, we're still using convolutional neural networks, and that we can consume images from both cameras as well as LiDAR. And the way we designed it is we would actually have two heads going in for the camera and then one head going in for the LiDAR. And we design a middle layer that we combine these two so that we can model the interactions. This is one way of learning about interactions between these two relatively different modalities of sensor. And actions, as I mentioned, are going to be the actions that we're going to take, such as go slow with 20 degrees steering to the right, go fast with 10 degrees to the left, and things like that. Let's go to the next chart. Now imagine that you have this neural network in front of you, and we kept the middle and the last layer intact, but we changed the input layers. So at one point we had 3 CNNs, at another point we had 7 CNN layers. And this is where I say where you have to be really careful with the reinforcement learning, and what you wish for, you may just get it. So in the left column of plots, we have a simple reward function. And when we say simple reward function, what I mean is that stay on the road, and I'm going to keep giving you rewards as long as you stay on the road. And if you stay off the road, I'm going to give you 0 or no negative rewards, right? So which is a very simple reward, but by being simple, it's also nonlinear, right? You're either getting a lot of reward or you're getting no reward at all. There's nothing in between. We learned, for example, that if you look at these graphs, that when you have this nonlinearity, you can't get away with shallow neural networks. The convergence is very slow. You're going to be spending hours and hours on the clusters trying to learn this. But if you have a deep neural network, you're going to learn this pretty fast. And the number of episodes corresponds to the number of episodes it will take for the car to learn. Each episode being that you either get out of the track or you stayed on the track and you completed. But if you look at on the right, we designed what we call in the reward function, advanced reward function. By the way, if you're really excited about learning about reward functions, there's a big Reddit community on AWS Deerpacer Reddit community where people had published their reward functions that were winning in the summit. So I strongly encourage you. It's a 20 line of Python code. And in some cases, it's 5 lines of Python code. And in some cases, it's the 15 lines of Python code. So it will give you a good idea about what people are thinking. In the advanced reward function, what people did was, oh, I'm going to say that if you're close to the yellow dotted line, I'm going to give you a reward 10. If you're away from it a little bit, I'm going to give you a reward 5. If you're getting close to the white line, but you didn't cross it, I'm going to give you reward 2. So you can imagine that as I go away from this yellow line, which is the safety, safety line that you stay on the road, that you get gradually less and less and fewer rewards. So in this case, you can actually get away with shallow neural networks and you don't have to get a deep neural network. And the difference is that, why do I care about shallow and deep network? This is a huge problem when you're designing hardware, because the inference, the time that your neural network is going to give you an output, given an input, is very critical on the hardware. You do not want to be slow. You don't want to be slow to act in your hardware. And you cannot be too fast. If you're using a deep neural network, it's going to take long. So these are kind of the trade-offs you'll have to make in the hardware when you're thinking about implementing these AI algorithms in the field, in the real world. So I have about 10 minutes. Is that correct?
Yeah. So yeah, we have 10 minutes, maybe like 5 minutes left for questions and answers.
Okay, so what I'm going to do is let's roll through the next charts very quickly, and I'm just going to point out very few important things. So simulation to real world. Let's go to the next chart. One of the things that I really would like to emphasize is that, remember I talked about it is really important to do unit tests. It's really important to go back and forth. And the reason that I'm saying it is important, because it really helped us move really, really fast. We didn't wait for the mechanical parts to be right. We said, let AI learn the discrepancy between the mechanical parts. And then the next thing that we said was, but how can we ensure that the neural network is actually doing what it is supposed to do, and we're not just getting lucky with some of the experiments that we're running? So it really helped us to start early. And when we started early, we not only came up with tests and metrics that we can create in the simulation environment, but we also developed mechanisms that we can collect and store data and analyze it on the car. So we kept iterating on this. And one of the very useful tools that we had was GradCam, that we were able to overlay on the GradCam how the neural network gradients are learning. So this has nothing to do with the reinforcement learning, but it has a lot to do with how you can guarantee your neural network and or get an idea about your neural network is doing the right thing, and you're not just getting lucky with 2 or 3 experiments that you had run. So what we did was we said, okay, we're just going to have small number of experiments, but we're going to analyze the data, and then we're going to go back and run a couple more experiments, and we'll have this cycle. So what we learned from this one is, you can see that in each group here, in each chart here, you're actually seeing the actual image overlaid with the GradCam analysis. And it really provided us where the gradients are paying attention. And what we also learned is that some of the algorithms, some of the reward functions were learning better. Some of the neural network were learning better, even though they had shallow layers given the reward function. So what we started doing is that we analyzed this GradCam outputs, which told us that these are the kind of things that your neural network is learning. in addition to other metrics that we looked at, such as the similarities, mean square error, and things like that. A simple visual confirmation is sometimes what you need to get started with. So don't shy away from saying that I need to do too many unit tests. It's a great learning experience. Let's go to the next chart. And here's actually the outcome of it, that by running these unit tests, we had actually collected lots of data. And what we also learned was that why don't we try different kinds of colors on the road? Why don't we have headlights and things like that? So now that you have a base product that is working and doing the right thing, now you can start making your product complex. Always start simple. Always start simple. And what we then learned is, okay, our simple neural networks, we started simple, weren't able to get away with these flashlights, which we thought they look like the lights of a car that may be coming from another direction. And what we learned is that we can actually marry the convolutional neural networks with attention networks that are actually the essential part of what you hear today, transformer models. And using these attention layers prior to the convolutional neural networks, we were able to capture where the car needs to pay attention or focus on when they're learning to avoid lights, when they're trying to learn in a dimmer setting. And another thing that we learned was that we were able to come up with a theoretical equivalent of this, which is in the, if you look at the literature from early 2000, you will see that servoing, visual servoing is a concept that is highly studied. And attention neural networks married with the convolutional neural networks actually map into the visual servoing that has been studied in control system society and literature very well. So we also were able to find this theoretical connection between the two that enabled us to tune our attention models a little better than others. Let's skip to the next chart. So this is supposed to be a video that you can see the car in action, but I will provide my PowerPoints later, but you can also look it on the internet and search for Deep Racer and you will see these videos. Actually, I highly recommend that there's another video called Deep Racer Night Rider. So if you find that video, you would actually see that the car navigating in dark. Let's look at the next one. So I'm actually going to so another thing that we did also was at NeurIPS a couple of years ago. We partnered again with AI Driving Olympics. So here is a video, and this video shows that the stack that we designed for you, that you can actually get started open source. You can get the gross node spot for simulation, as well as the hardware on the car. You will see that if you look at the videos for NeurIPS 2019 Deep Racer, you will see that we start out with this, but the car goes out and goes onto the carpet. So different textures and different road types all jumped or jellied in together, and the car can still learn very quickly. Again, it's the same thing. Train it on the simulation environment and then copy paste your neural network literally onto the car via USB drive. Let's go to the next one. Next one. So what I would like you also to go to look at is, after we started simple, we again thought about how we can make this more complicated and engaging. So we started this multi-agent reinforcement learning approach, where now you have multiple cars driving on the road. But the thing is that, remember, in the simulation, you're kind of like a god, that you have access to all the information. But when you're on the track, you don't actually have access to the value functions and rewards that the other cars will see. So we developed a method which is called robust multi-agent reinforcement learning, which we presented at NeurIPS last year with the theoretical results on convergence. And this is currently one of the approaches that we take in multi-car racing. Next one. And this is a video where you can see this in action actually. So if you go to internet and search for Deep Racer Reinvent multi-car racing, you will see that the cars are racing and passing each other and so forth. There are tons of videos out there. Let's go to the next one. Let's go to the next one. This is the link to the paper that you can read. I'm not going to go into the details here, but if you're really interested and you want to know more, please reach out to me. So let's talk a little bit about how you get started. All our stack currently can, there's actually a service, AWS Deep Racer, but there are also SageMaker notebooks that we had provided and open sourced, and you can basically get started with the stack in a couple of minutes, and the cost is several dollars. It's for you to get started and training, and if you want to spend a little more time, then we also have resources that enables it. I highly recommend go check out the software stack on AWS, and also there is a huge Slack community which I will provide the link, and this is community community Slack channel outside of Amazon and AWS that gives you quick tips on other things that you can do. Let's go to the next chart. So here are the resources. So the Pacer Slack community, you can join in. There's no conditions on being part of the community. But if you do something really exciting, please let me know, send me an email. I would like to know. And we do have lots of examples on GitHub and lots of free video courses that you can take, and some tips from other racers that you can also find out. And we also created tons of blog posts that you can go and look into to learn more if you would like to deep dive into Deep Racer. Let's go to the next chart. I think that's my final one, and which is a shameless advertisement. We as an Amazon and AWS, we're really excited to be part of the growing community of ML practitioners. And we sponsor events at conferences as well as communities. So we would like you to participate and let us know how you feel about the code that we had put out there. And I would like you to really check out the NeurIPS 2021 RL competitions. If you want to learn about reinforcement learning, it's a great opportunity. Why? Because we give you a starter code. You don't have to start from scratch. And our starter code for the NeurIPS competition, you can run it locally on your computer. You can run it on AWS Cloud. It's up to you where you want to take it. What we really want to do is for you to learn from the tools that we're providing and give us feedback. With that, I'm going to pass it to Tarikur. And thank you so much for listening. And if you want to learn more about anything that I had talked about today, please contact me on LinkedIn or reach out to me via email. Thank you.
Thank you so much, Sahika. I think we have time for one question in here, but if the subreddit link is not in the slides, can you put those in there? Terracor is going to put the rest of those links into the chat for us. But before we let you go, I wanted to share Terracor's question here. How do you determine a good reward function? When should I use the 5-line versus the 20-line code?
Yeah, this is really it actually goes to some of the graphs that I was providing with the number of episodes. Basically, what we do is we do have CloudWatch metrics, and this is also something that you could also get locally when you're running Deep Racer, is that you will see how your reward, how your total reward across the number of episodes that you will be getting at each iteration of the algorithm. So what we look at is when those rewards stabilize. Other than that, there is really no way of knowing by just looking at the 5-line or 20-line whether it is good. So again, as data-oriented people, we look at the data. One other thing that we look at, as I mentioned, that this is one of the key components of reinforcement learning, is exploration. So we actually look at the reward and exploration graphs together. Deep Racer currently use clipped PPO, and that method is based on entropy-based exploration. So we look at the entropy along with the cumulative reward at each iteration of the algorithm during that feedback loop. And we look at when the rewards stabilize to a certain degree. And then we look at the entropy. And finally, then we look at comparing the times. So for Deep Racer, you will see something called leaderboard. And in that leaderboard, you will see your timing and the reward that you achieved. So basically, it's not easy to learn it from again, it's a trial and error. And look at the output data, reward exploration, and literally checking if your car is doing the right thing by watching the videos.
All right, thank you so much. And I was amazed as I looked at all of the stuff that you have out. You have so many papers published. I did want to ask, did you have a favorite paper?
Yes, actually, our recent paper in ICML, it is about something that we learned from our participants and community. So people were saying that, well, I trained my model on the London loop, and I had a really good model, and I want to use it on the Tokyo loop. Will that work? And I'm like, I don't know for sure, but we could give it a try. We kept getting these calls saying, okay, I really would like to see that I can use my really, really good model. So the ICML paper is on reward transfer learning. It means it's a method that we developed based on a few other transfer learning methods, which allows you to learn from the past models and experiences. And one thing that is really good about that model, we tested on StarCraft, and we are really good at transferring your StarCraft models. So I highly recommend checking that paper out.
Thank you so much. All right, and with that, I'm going to introduce our next speaker here, Bam Adele. Can we hear from you here?
Hi.
Hello. Go ahead and see if you can share your slides for us, please.
Okay, I'll just check that real quick.
It looks like TerraCore got a lot of those links in there. We will also be sharing slides on LinkedIn and Discord channel for anyone who was asking for some of those things earlier. Go ahead. Are you set?
I'm trying to. 1 second. I just tried now. Try to share the desktop. Okay, hopefully. 1 second. So I think it's kind of trying to check for privacy. So
if you want, I can share it. And then...
Yeah, I mean, you can share it. So I'll just you would just help me kind of navigate through the slides if that's okay.
Awesome. Yeah, no problem.
I'm glad I had to send that to you.
Yeah. Sorry for the technical difficulty, and thank you everyone for joining.
Yeah.
All right, I will share my screen.
That's good.
Everybody sees it?
Yeah, so you can start from the first slide.
Good.
Yes, thank you. So good afternoon, everybody. My name is Bamidele Ajisagun. So I'm a PhD student of Robert Morris University here in Pittsburgh, Pennsylvania. I'll be talking about the application of machine learning in detection of inflammatory myocarditis in patients with high susceptibility to heart failure. So just a background before we go in. So I kind of, feel like a lot of things are happening, and it's very important for us to kind of use um, our artificial intelligence to kind of drill down and dig deep into how its application in healthcare would be really important to us. And this is one reason why I have decided to, do a research in something that it's really rare, and a lot of people, kind of find it confusing. Even our medical practitioners kind of find it really confusing to kind of really map out, the cause of myocarditis in patients and then how it has led to heart failure. Next slide. So, like I said, this is a research in progress, and the question I'm asking is, how can early detection of this myocarditis, using machine learning algorithms help prevent heart failure? So, because I know that this disease leads to heart failure. So, from research and literature, we understand that myocarditis is an inflammatory heart disease that leads to heart failure. I'll be explaining about it real quick. I just wanted us to have like a conceptual understanding of why this is really important. And what's the problem statement? What am I trying to solve? So I understand that myocarditis is an underdiagnosed cardiac disease that leads to heart failure because of the inability to diagnose it early and the uncertainties in the disease itself. So it's very, very difficult to kind of diagnose that disease really early until most times it gets to the acute stage. And to some people, it just causes sudden death, cardiac failure. And then people are like, oh yeah, well, what's the cause of this? So the purpose of my research study is an early prediction of myocarditis and identification of uncertainties in patients using machine learning algorithms. Next slide. So just a brief introduction on the broader scale. So there are wide ranges of heart disease, and the most common ones are the cognitive, which is the congenital heart failure, heart disease, CHD, the coronary heart disease, CAD, the heart arrhythmia, the pulmonary stenosis, and the dilated cardiomyopathy. So I'm highlighting that part of dilated cardiomyopathy because that's the area that we would be talking about today. Next slide. So in the course of my PhD research, I kind of did a mental model of the growing literature review to kind of understand how or why this is happening. So what I did was I had a conceptual mapping, and that's why you can see right here, you can see the sub concept one, sub concept two. So I kind of, drilled into the two funnel by trying to understand what the prediction of heart failure from myocarditis is, and then how do you apply machine learning as a tool. So I did broad to narrow, and then I kind of mapped out, identifying the problems using research and then providing solutions as well using research. So on the left side of this slide, you can see how I kind of did like based on chronological order, what the conceptual understanding of how to apply machine learning as a tool. And then on the right side, another chronological order from old to recent, how the problems that have been identified from broad to narrow, and then how we can provide a solution. So at the end of the day, we want to kind of understand what the problems that needs understanding, the right data to be used, and then how can we prevent this heart failure through early detection of myocarditis. Next slide. So first, we need to understand the three types of heart inflammation because it's very important to us, and that's why I kind of define based on literature the pericardium, the myocardium, and the endocardium. So the pericardium is the outer layer of the heart, and that's like the sac that connects the tissues surrounding the heart. So it's kind of like the like the cushion area that surrounds the heart, and then that's where you have the nerves and the blood vessels that supplies supports the heart. So and if there's an inflammation of the pericardium, that's when you have a pericarditis. So and that leads us to how I have been trying. I'm trying to kind of give you like a picture view of how this works. The outer part is the pericardium, and then we move to the middle layer, which is the myocardium. So and that's where you have the muscles of the heart. So, and the muscles by itself, they expand and contract, in the myocardium, and which enables the heart to pump. And when people do their blood pressure, you see the systolic blood pressure that helps to pump, and then the one that helps the heart to kind of feel and relax, which is the diastolic pressure. So in that middle area is where you have the myocardium. And if there's any inflammation in that area, it is known as the myocarditis. So, and then the innermost layer is the endocardium. And then in this area, it's the inner layer, which also has like, connective tissues and the organs and linings and, the heart chambers, and then the valves and all in there. So if there's any inflammation in that area, it is known as the endocarditis. So, but for this purpose of this research, we would be talking about myocarditis, which is the inflammation of the heart muscles in the myocardium. I hope that's clear. So let's move to the next slide. So this is kind of like the anatomy of what you expect this for normal heart and an inflamed heart. So Sarah, can you please use your mouse to show on the right side? No, don't click, just where you have the myocarditis, go down a little bit. Yeah, you can see, right. So you can see that whitish part. If you move your mouse, yeah, you can see that area. That is what causes the inflammation. So the myocarditis, that which is from, actually when viruses enters the body, okay, so the body has some autoimmune response, kind of want to fight these viruses, and then this virus kind of moves towards the heart. And when it gets to the heart, depending on the type of virus and all that, so your immune system automatically wants to fight these viruses, and then that's why you kind of have like an autoimmune responses, and then the cells within the heart as well want to kind of fight, and all of these kind of causes inflammation. So, and that's why you see that area where it's kind of whitish. I wish I had the mouse on so I could show you around. Sorry about that, but you can see, like, you can see the zoom in part where Tarek is kind of showing right now. So that's where, yeah. So that's the myocarditis itself that kind of inflames the heart muscles. You can compare the regular heart normal anatomy with a fatal condition. You can see that it's really dilated in the left ventricle area. It is the dilation also in the right ventricle area. So it kind of really causes a lot of issues for the heart, and it makes the heart difficult to pump. And before you know it, there's an imminent heart failure. Next slide. So, like I was explaining earlier, what causes myocarditis? I said it's caused by viral infection, which could be common cold, hepatitis B, parvovirus, herpes simplex virus. There are a lot of viruses out there that kind of causes myocarditis. Literature has also revealed that bacteria, such as diphtheria and tick-borne bacterium, could be responsible for some kind of diseases around that myocarditis area. Fungi and yeast infections too could be. Parasites such as trypanosoma. They are also, relevant causes as well. So other contributions, that could cause development of myocarditis are because your autoimmune, is kind of working. Your autoimmune system is kind of fighting against those viruses. Your heart muscles begin to get inflamed because it's trying to fight. There's a pressure, somewhere kind of inflaming the heart muscles. Exposure to certain kind of chemicals, such as CO2s as well. CO, carbon monoxide, are also really causes of certain radiations in your body, and certain cancer and seizure medications as well, use of cocaine, vasculitis. So these are like all the contributions to myocarditis. Next slide, please. So in time, we just explained about myocarditis and inflammation of the heart muscles, and then we said that it's in the middle layer of the heart. And then we said it's as a result of an infection or something, other causes that may trigger it. So from Thuspo et al., if you look at in time, in the 1950s, what kind of viruses were we looking at? We had antiviruses, influenza viruses. Those were the common ones early back in the day. And then in the 70s, we had other kind of viruses like the cytomegalovirus. In the 80s, HIV was really prominent. So these are kind of viruses also that goes into the heart and causes the heart to get inflamed as well, because the cells, the autoimmune response, are kind of fighting that viruses. And then there's this, that reminds me, there's this research that I'm going to be working on, which is the ability for the body to cure itself from HIV. That's like an autoimmune response for the using deep learning, using deep learning to predict how the body using autoimmune response to fight itself and away from HIV. So that's like a pending research that I'm also going to be working on. So as we move towards the 2000s, we had the HPV virus, the herpes virus, the SARS, and then in the 2010s, we had the hepatitis C viruses, and then in 2020, the COVID came. So all of these viruses kind of, have influence on myocarditis. And then the research on COVID and myocarditis is something that is ongoing, and then we're also working on that as well. So how this also has different phases. We have phase 1, which is the initial myocardial injury, and then we have another phase 2. First when you contract the virus, and then the phase 2 is when your immune system start fighting. So there's a myocardial injury, and then if it's not treated, it goes into the phase 3, which is a dilated cardiomyopathy, which is that inflammation that we have looked at earlier. And at that point, there's a sudden heart attack or sudden death or heart failure. Next slide. So like I said earlier, myocarditis and COVID-19, it's somewhat related, and then we are kind of, examining what the, based on cardiography, cardiac blockers, and then CMR imaging, to kind of see how myocarditis is being affected, or it's a function of COVID, and see how both of them, how COVID can be a reacting agent to myocarditis. So this is an ongoing research as well. Next slide. So what we did, what I did was to do a core idea map of myocarditis using machine learning. So what I try to do is I try to do my 2 funnel as well. I try to look at what are the research questions I'm trying to solve. How would machine learning and AI help me in solving those problems, and what solutions could be tested? So, using deep learning and all of that. So how, would I be able to use this process to kind of map how myocarditis is, its occurrence and kind of early detection, to see where the right ventricular dilation and that dysfunction occurs, where you have the left ventricular dilation occurring, and then your pulmonary hypertension, which could happen as a result of this inflammation as well. Next slide. So gap analysis and early detection is really critical to kind of understand where we are. So based on medical research, what is being used in the medical industry currently is the CMR imaging, what is used for this detection and mapping. They use the echocardiogram, they use the nuclear imaging, the coronary heart angiography imaging, and then the endomyocardial biopsy. So these are like what is currently used. And at this point, where this medical gadgets, are being used, it's already getting towards the dilated stage. It's almost getting to a stage where the infection or the disease is already, at almost the acute stage at that point, because it wasn't detected early. Your CMR wouldn't detect it like in the earlier stage, like in the first stage, you know what I mean? So your echocardiogram could even read right readings in the first stage, because all the signs, the clinical signs you might be seeing could just be a chest pain, and people overlook that, right now, because they just, feel like, oh yeah, I just have a chest pain and that's it. That's not it. You need to go like really, really deep, do a deeper dive of why you're having a chest pain, because you wouldn't just have a chest pain if there are no underlying conditions. So artificial intelligence using machine learning is really critical. We have different methods that you all know. We have supervised, the unsupervised neural networks, and deep learning. So basically, the neural networks and deep learning would really help in this area, because your neural networks, deep learning is kind of representative learning that would, kind of improve your cardiac imaging analysis and all of that, because the more data we have, the more classification we'll be able to get at the end of the day. Next slide. So based on what I was explaining earlier, so the severity is kind of, different from mid, moderate, and, highly severe based on what stage. At the mild stage, it's usually, you could say acute, early stage, 3 months, moderate, 3 to 6 months, and then anything after 6 months becomes really severe. So, and this is really critical that, this can really, really kind of affect life as well. So what are the clinical manifestations that I was trying to, explain the other time? You could have chest pain. 95% of patients with myocarditis would have chest pain. What is the white count elevation? What's the sedation rates? What's like your EKG reading? And all of that. Next slide. I'll explain with the chest X-ray as well. So your ECG also could help you, at the later stage, kind of see where your how your readings are, and then would help you detect myocarditis at that infarction stage. So Tarek, if you help me put the cursor at where you have the myocardial infarction pattern, that takes it to the upper right side, upper right of the.
I think you can control my screen. Can you?
Let me see if I can take control of your screen. Okay, wait, you control the view options.
But that's all right.
No,
Top
I don't.
right.
Yeah, I don't think so. Yeah, so upper right side, you see where the arrow is. To your right, you see how the sinusoidal. If you see how where this arrow is pointing to, you see where the sinusoidal value is. There's a large curve up there to your right. Can you see that, Taco? I'll just go on. Yeah, I'll just go on. Yeah, like I couldn't have control of the screen, but yeah. So, so that's particular infraction, would, kind of, yes, that's point. Yeah, to your right. Yeah, the next one to your right. Yes. So yes. So that's how you can be able to identify a myocardial infraction pattern, through your electrocardiogram, and that stage is not the early stage. You see what I mean? Because that means there's a myocardial infraction already, from the myocarditis. You know what I mean? So at that point, they start, using medical manifestations to kind of, see where that is. Next slide. So we can medically too, we can measure X-ray, based on your cardiothorax index to kind of calculate what the City.AI of the chest is based on, based on this inflammation. You can kind of see whenever you have your left ventricular systolic dysfunction, City.AI, to be greater than 50%. That means there's something wrong. And if you have your diastolic dysfunction, City.AI, to be less than or equal to 50%, it also means that something is wrong. So at the normal stage is 50%. Next slide. So I would quickly touch on a case study here that kind of using machine learning algorithms to kind of see where we are with the prediction of myocarditis, and which is also known as inflammation of the heart muscles, using advanced machine learning algorithms. Next slide. So this data set was by Sharif Razi. So we kind of reviewed this data set. So he applied convolutional neural network and combined with K-clustering, to kind of use that to predict myocarditis in patients. He also confirmed that it's a cause of death in approximately 20%, and then in less than in adults in less than 40 years of age. And to let you know as well, myocarditis is one of the leading cause of sudden death in athletes. Sometimes when you're watching a football, or when you see the athletes and sudden cardiac arrest, sudden death, sudden heart failure. So more often than not, it's from an imminent myocarditis that wasn't treated, and that was why in one of the journals that we read, when myocarditis is detected, people are stopped from any athletic gain, And then it also happens in children in new childbirths as well. So this disease is really, really rare, but very, very critical to kind of understand. So this data set that was used, was used to diagnose myocarditis. 47 patients were diagnosed from Tehran Hospital in Iran. And then the number of data sets were about 10,425 samples. And then the results showed that 92.3% were diagnosed, and 92.3% accuracy in the diagnosis of the myocarditis. And then, at the end of this presentation, I'll be showing you what would be our next step, to kind of improve this accuracy from 92.3 to about 95, 96, if possible, 97%. Next slide. So this kind of like a block diagram of, it's not really clear, sorry about that. So it's like the block diagram of the proposed, convolutional neural network, and then the K-clustering method that was used. So of course, at the first step, the data sets, moves into the system, and then the second step would be your initial preprocessing stage, where all the data are kind of reprocessed and resized, because most times you might have data set of different sizes, so you can size by 100 by 100, and then upon resizing of these images, you can normalize them. So you can do your normalization of image transformations, and then you can have your image pixel from 0 and 1. So it can kind of like filter, get the better understanding of your image. And then there are different methods, for clustering your data as well. So K-means method is used to cluster your image. I'm sure we all know that. So, and then at that point, you can divide your data. This data was divided into 2, 4, 10, and 24 clusters respectively, by the K-means algorithm. So, and then the next step was to, kind of do a, for each cluster, using the convolutional neural network, kind of explain what the features and then how they are fully connected in the layers, and then afterward the classification of the clusters, they were displayed, respectively. So, and on what you see on the right side is kind of like a general architecture of what the convolutional neural network would look like. And then you can see the input data on your right side, and then you can see the convolution, and then max pooling. I'm sure we all know this. So of course, in our neural network, you can have an input, and then you have so many hidden layers, and then you can have like an output. So at the end of the day, what this architecture of this convolutional neural network did was, we were able to kind of have an output that the green 0 and 1, the green means healthy, and the 1 represented that there is myocarditis. So this research paper actually integrated both the CNN, the convolutional neural network method, and then with the clustering method. Next slide. So in terms of trying to explain the results, so the first step was to, like I said, was applied for classification purpose, which I tried to explain earlier. Also, an elbow method was implemented for 1 to 30 clusters. So, and that's where you have, the elbow method, the importance is to find the best number of clusters, so which would, for this reason, they had like K for the 10 and 24. And then for the K4 clusters, you would have 2 healthy people, 2 sick people, and then the K10 cluster would have 5 healthy people, 5 sick people. for the K24 clusters, we would have 12 healthy people and 12 sick people. So this was kind of like, try to divide, kind of separate the clustering. And then the result that was obtained showed that the K4, kind of gave the best results, and in the ratio of 20 to 80, 20 data sets and then 80 training sets. Next slide. So this is like the ROC area, which is usually used to select a threshold for a classifier, which maximizes what the true positive is, and in turns minimizes what the false positive is. So this was like a guide to help to kind of see what the accuracy of what the model that would be generated, kind of compare to see where we are, and then this also kind of help you to determine what the exact trade-off between what the true positive rates are or what the false positive rates are in modeling. Next slide. So the accuracy for the convolutional neural network and then the K clustering were different, for number of clusters for 70 to 30 training sets. And that's what I'm showing here compared to the 80 to 20 training sets. That's 80 training data and 20 real data, so the results were compared. So the results show that the accuracy in the 30 to 70 mode, it's was not as great as the accuracy for the 80 to 20 mode, which I'm going to show in the next slide. So each of these figures kind of show the result of 4 clusters, 10 clusters, and 24 clusters. So the blue and the orange lines, if you can show the blue and orange lines, so they represent the training and validation process over 70 epochs, respectively. So next slide. So let's see how the other, so this kind of, gave a better results, for the accuracy using the deep neural network based on how the machine was able to learn from the data set and was able to give a better result. So this data set, for example, obviously has its own limitations, but for this purpose, I just wanted to use it to show that literature have proved, or theories, based on research, that we could actually use these deep neural network methods to kind of be able to predict myocarditis and in medical investigations as well. Next slide. So this was the results of the CNN and the KCL, and using number of clusters. So if you look at the middle area, Tariq, can you put the cursor around the 4 clusters? So the accuracy, for the 70 to 30 data set was 91.9, and the accuracy with the 80 training data sets and the 20 real sets was 92.3, with the loss ratio of 0.301. And an F1 score of like 4.5, so which is really impressive as well. So so this also kind of buttress the fact that machine learning is useful in this application as well. Next slide. So this data sets, confirmed that myocarditis remains one of the most challenging diagnoses in, cardiology, and how it affects the heart muscles and the electrical systems. And then it's very important to know that, the convolutional neural network and the K clustering, when using the 4 cluster mode, demonstrate the best performance compared to other modes. I didn't have to show all the other modes here. That was just like a lot of data. And then the convolutional neural network and then with the K clustering can achieve a better results of in terms of accuracy, precision, with a better F1 score and lesser loss, respectively. So the next level for my research would be, utilizing a deep reinforcement learning and supervised methods such as recurrent neural networks, the RNN. So which is also, is also something that is currently in the evolving now, because a lot of medical research data scientists are also trying to see how recurrent neural networks, would enhance the prediction performance and would help increase the prediction accuracy compared to what we have here currently. And, that's more like your reinforcement kind of learning, and, the contribution to knowledge, would help improve the information systems that we currently are in. So, and then I would also aim at using explainable AI case-based reasoning method as well, because that also is really evolving as well, and especially in diagnosis and in research in medical. In our medical field, so case-based reasoning is a very good method that mimics the way doctors kind of do their diagnosis. So, and the importance of this is that we want to try as much as possible to be able to detect, to be able to detect myocarditis early in patients enough before it gets to that acute stage. We want to be able to use our deep understanding, of machine learning to actually train the data sets in such a way that even with the least amount of variable that we have, such as just with chest pain, we can map what type of chest pain leads to, myocarditis, and, how does this, kind of, because we don't believe that anything randomly happens, for you to have a manifestation, there's something underlying. So we need to map, early enough that underlying disease or symptoms, or attributes in data science, as we may call it. Next slide. So my special appreciation to Daniel Sharifa's Department of Computer Science, Computer Engineering at School of Technical and Engineering in Shiraz in Iran. And then I want to, for using the data sets that I just showed. So I want to especially thank the New York AI also for this opportunity, so it just shows that there's a lot that can be done with machine learning, artificial intelligence, and like I explained earlier, so I have research areas that I'll be working with, and I explain, some of which is, explaining how HIV can be cured, self-cured by the autoimmune system, and this is really critical. And another interesting research that I'll be working on is the prediction that a patient, somebody will die during sleep. We see that some people sleep and they don't wake up anymore. So there are some underlying illnesses that, that are not manifested, that we don't even know that we are having, but, the person just goes to sleep and that's it. So we want to be able to use our deep learning approach to predict the probability that somebody will die during sleep. So these are like innovations that we are trying to do as well. And another one is in cancer research areas, which is really critical also for our well-being, trying to understand, why cancer is happening, the critical approach to diagnosis in the early stage. Thank you all.
Thank you, Bamidal.
Thank you.
I know you have to go, but do you have like time for a question or two, or?
Oh yeah, was I on track with time?
Oh yeah, you're good on time, but
Okay,
I know you mentioned earlier that you had to step out. At
like
like
it's because of work, but yeah, I can take questions right now. Yeah, sure.
Okay, awesome.
Any questions? Yeah, so if there are any questions or contributions, or just anybody willing to join the research on myocarditis, feel free also to contact me. You know what I mean? Like we can do a lot, with AI and ML. So yeah, feel free.
Yeah, I'm very fascinated. And actually, like, yeah, all the slides and stuff, I'll definitely share in our Discord and also our website as well too, so they can reach out to you.
Mm-hmm.
Actually, I had a quick question. So like use k-means, right, as the clustering. Did you use as like a additional feature after your CNN?
Yes.
Like,
so,
or
yes.
did you like use it as like a final layer?
So what happened was during the process of understanding how or where we should apply that, because normally you could use your convolution neural network by itself, and you could even use your case clustering by itself, but to kind of have like an integrated method in this area where you can slice in where your CNN kind of precedes your K clustering, or your K clustering precedes your CNN. So in this case, so it's important to kind of understand how the K clustering works for the different clusters by which precedes the neural network, because at the end of the day, also what we're trying to achieve is, we know that the more data we have with the neural network, the better the results as well. So it's also, it may be realistic to maybe identify the different clusters that would give the best results, and then you can put that into your convolutional neural network, kind of precede one another, and then see how, the data that you're having, just to confirm what your clusters are saying, based on the initial data that you're putting in. And for me, I feel like it depends on what you're trying to map eventually, so you can use them by themselves, but I don't know if, what the probability of having the required results would be. I've seen data sets where a convolutional neural network was just used in machine learning, and we could be found the prediction rate to be about like 3% accuracy, so which is also good. The neural network by itself, or the representation neural network by itself can do the job, but it's also good to kind of apply K clustering and see how we can classify this whether seek or not seek data.
Okay, awesome. Thank you.
Yeah, thank you.
Thank you so much.
Yeah, thank you.
Awesome. All right, so we can segue to our next speaker, and I'm pretty happy about the next speaker as well too. And yeah, I'll let Shanna give herself a little intro and what she'll be talking about today.
Awesome. Can you guys hear me and see my screen? If someone can audibly say yes.
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 Awesome. Thank you, because I have my speaker notes to keep me on track, but I can't see all of you guys' great pictures and faces, but thank you so much. Hi, everyone. I'm Shayna Lee. I work with Datakind. I'm based out of Atlanta, Georgia. So really just want to thank everyone for the opportunity to speak with you all today about the art of the possible, creating data science solutions to ultimately serve communities. And I, at Datakind, I work with our pro bono volunteer community to ensure that they ultimately have a positive experience as they are engaging with us on various projects and events, that they have the resources they need to be successful in that regard. So what is Datakind? For those that may not be familiar, Datakind is a global nonprofit based out of New York, whose mission is to harness the power of data science and AI in service to humanity. And so what we do is we help social organizations identify their data and AI opportunities. We recruit and partner with the team of pro bono experts or volunteers to help build those solutions. And we stick around to ensure that the solutions are used and the impact that was defined is achieved. And so as we enter our 10th year anniversary, we're pretty excited about our accomplishments thus far, while recognizing that we do want to do more and see how far we can go in the future. We're proud to say that we've engaged over 20,000 community members around the world, including 5 chapters. We've had over 250 events with volunteers that represent over 174 countries come together to work on data science solutions. We've been able to complete over 350 projects supporting 186 organizations. Again, all in thanks to the contributions of our pro bono expertise and time from our volunteer community. If you keep hearing about our amazing volunteers, that is intentional, because they are the heart of being able to fulfill on our mission. And so, as I've mentioned, we have 5 chapter locations currently that are led by volunteer chapter leaders who have helped foster our movement and impact. They're located in Singapore, Bengaluru, India, the UK, and in the US, Washington, DC, and San Francisco, respectively. We definitely get inquiries into how there can be additional chapters, and we are working on those inquiries and what that strategy looks like for our expansion. So with that said, our organization works on wicked problems, as you can see here in this quote, defining a wicked problem as one that is difficult or impossible to solve because of incomplete or contradictory or even changing requirements that are often difficult to recognize. And so you'll see here by this visual, this is our approach to those wicked problems in a way that can be built to create global impact. This theory of change illustrates how innovative solutions can make a sector and a global impact. And noting here that our work doesn't just end once we build a solution, we collaborate with our partners to adopt, scale, and share across sectors. And so one of the observations that we've had in building and executing data for good projects is that we found 6 components are necessary for success that you see here: a problem statement, data sets, data scientists, of course, funding, subject matter expertise, social actors, or you can interchange that with communities as well. And this is ever more true how necessary these components are as we look to bring a solution to an entire sector or industry rather than just an individual organization. We look for problems that represent shared pain points through discussions with our subject matter experts and actors. We know that trailblazing funders, for example, are key to helping diffuse the risk of new solutions, and they're essential to platforming and scaling those solutions. And as we identify, build, and execute projects with a goal of globally valuable solutions using the available data and working with teams of those expert data scientists, we need to identify these components to mitigate the risks that may prevent us from achieving our impact. And we must do well when identifying and partnering with each of these components, as well as the collaborators, in order to continue to create those high impact programs and solutions. And so when collaborating on a project, here are some of the elements that we seek within a visionary partner organization. We do look for those that are mission driven, those that are nonprofits, foundations, charities, social enterprises, and government agencies, those that have a clear theory of change and understand ultimately how their activities lead to real world change amongst the communities that they serve, that they have digital data or know of unexplored open data sets. And also a critical component is those organizations that have leaders committed to using data to make decisions, that are able to learn hard truths that may come up through a partnership, not just to report on what the work that has been accomplished. And you'll see here on project outputs here, this is not an exhaustive list of outputs, as we recognize that we define what those outputs look like specifically in conversations with partners, but these are common ones that we see. Being able to answer questions to some of their most pressing needs, findings to cut costs and improve efficiency, improve systems to help staff deploy resources, or algorithms that can help predict future needs to better allocate resources. All of this really driving towards how this can help the communities that they serve. And so I'm going to share on this next slide a snapshot of when we work on a project with an organization, what our project process looks like and the stages that it goes through. So this first one being discover, we essentially discover alongside a potential partner organization if there would be a mutually beneficial partnership opportunity. This can oftentimes take a couple of months, hence why we call it discovery. We don't want to rush that process on either side. And then afterwards, we go into the design stage where there's the opportunity to explore the data, dive into the partner's challenges, what their goals are, and design a project accordingly. The next stage, prepare, recruiting and preparing the team of those pro bono data scientists and project managers that would be necessary to help execute on the project, thus leading to the next stage, execution, where the team and partner work together to actually do the project, starting with a prototype that is adjusted based on feedback and needs and any adjustments that come along the way. The next stage is share. The team delivers the final version or product and documentation to the partner organization so that the partner can adopt that solution as well as monitor for impact and provide feedback, leading to evaluate, where we check back in with the organization later to reflect on what worked and where we could have done better. So, in what ways have we worked on our projects? We've offered a range of opportunities for involvement that meet the needs of the project partner, the volunteers that we work with, and companies as appropriate. The first being impact practices, which are long-term projects that convene multiple stakeholders to develop cutting-edge sector-wide solutions. We have two impact practices that we've decided to focus on. One focus area of impact practice being the frontline health solutions, known to others also as community health worker systems. And the second impact practice is around economic resilience. The second way of engagement through our projects is through our Data Core program. These are long-term engagements, typically 6 to 9 months, where we're able to support organizations through projects using data science to transform their work and the sector. This is a great opportunity where we have recruited volunteers. That typically occurs through an open call process where volunteers have the opportunity to express their interest. They can share their skills and experience through an application process. And typically for a Data Core project, we recruit across 3 different roles. We have a data expert, which are those that can actively work on the data science solution. We have a data ambassador role who leads those data experts, serving to motivate, unblock any barriers that they may have, and a project manager who ensures those steps are done in a timely way. Once those volunteer teams are built, again, they collaborate and work on those projects with the project partner for 6 to 9 months. We have our data dive events, recognizing from a volunteer perspective that while we have some amazing volunteers that are willing to commit long-term for that 6 to 9 months, we do also have volunteers that appreciate flexibility and perhaps want to work on something more short-term. So we have our data dive events. These are weekend-long marathon-style events that help organizations do initial data analysis, exploration, and prototyping. This is also a nice fit for those volunteers who have a variety of different data science skill sets. So for those volunteers that perhaps just learned a new skill and they want the opportunity to test it, we welcome them. For those that have more data science experience, we welcome those volunteers as well. So this is a really nice event to be able to be inclusive of volunteers from a variety of different backgrounds and skill sets. And then we also have community events. These consist of networking type events or quick consultations to help organizations begin their data science journey. I mentioned just a couple of minutes ago the fact that we have 2 impact practices. So I'd like to share with you an example of what the work looks like within our frontline health impact practice. So obviously, the question begs, why frontline health? Unfortunately, there are some sobering facts that have been discovered across the frontline health system sector. As you can see here, over half the world's, including 1 billion that are located in rural communities, still lack access to quality health care. There are 13 million children who go without a single dose of vaccines, as an example. There are unfortunately those newborns, children, and mothers that die each year from preventable conditions and disease. And according to the World Health Organization, they predict a shortfall of 18 million healthcare workers by 2030. So that really set the impetus for us to have several conversations with a variety of organizations that have the expertise, the insight, the knowledge to be able to share with us what's happening across global health and specifically the frontline ecosystem. Informed by these conversations, we've been able to target the work that we can do and offer to be useful and replicable across the global health sector. Again, not just a solution for any single organization, but really to the benefit of the sector at whole. And we're focused on designing with, not for, to ensure that the solutions offered are valuable as well as sustainable. And so listening from those experts and listening to all voices, including the various communities that are impacted, we've been fortunate to have over 100 conversations across these systems and organizations. We've heard of various problems that run the data science spectrum, from those that are not exclusively data scienceable, such as ensuring fair pay for health workers, to those that are novel and only currently relevant to a subset of actors within a sector, such as using image detection to identify settlements. So all of these solutions certainly are important. So we face the choice, admittedly a tough one, of identifying those that we think we can have maximum impact across the sector. And these are the four that we prioritize that you see here on the screen. Essentially, access to digital data, trust in that digital data, use of the data, and capacity to improve those data ecosystems. So here's an example of an impact practice problem that we worked on. And what we have found as a result of a pain point across the sector is that oftentimes frontline health teams often carry, for example, logbooks weighing 5 pounds or more to record healthcare interactions as they go about amongst their community. It sounds like it's a small issue, but in fact, it can take weeks or months for those records that are logged in to ultimately be digitized and for the data to be acted upon. And so this was an opportunity for Datakind, in this case, to partner with an international nonprofit called Writers for Health. Writers for Health essentially provides frontline services, and they complete paper-based data capture from required Ministry of Health forms. And one of the insights that we got from this organization is that it takes the Writers for Health team approximately 80 days from the time of collection to the time of digitization to be ready for analysis. So this represented a huge opportunity for Datakind to build and test an open source optical character recognition tool to cut down that digital conversion window from months to minutes. Here's another project we worked on. It was not an impact practice, but a collaboration opportunity that had emerged. With the Moulton Niguel Water District, they provide water, recycled water, and wastewater service to approximately 17,000 people across several cities in Southern California in the US, where droughts have also plagued those communities. And like many areas in the region, which is interesting, this water district doesn't have access to local water supplies. So they bear the cost of importing all of its drinking water supply. And when facing the worst drought that California had seen in the past decades, in fact, the district approached Datakind for more help to precisely and accurately forecast water demand in order to improve pricing, expand conservation programs, and implement initiatives to increase the efficiency of water transportation through its network. And so, as an example, one of the solutions that you'll see here, the blue line is forecasted demand shown with a confidence band. And the blue line shows any chance of reaching or exceeding maximum supply estimates. which is the red line that you see here, that ultimately will signal a warning to the district analyst. And at that point, they can predict anticipated demand down to a city block and thus use this information to better manage the water resources. So for us, success is when Datakind and its partners have created those solutions that are adopted widely and contribute in an impactful, meaningful way to sector level problems. That is something that we aim to achieve. And as I close out, I do want to share some design principles that we also use to help in our success. One, this may seem a bit obvious, so apologies if I may be sharing what's already known, but it can't be underscored and always needs to be made explicit and said, to listen from experts and listen to all voices, including the communities in which these organizations serve. It's helpful so that as we're co-creating what those solutions look like, that it's meaningful and adoptable by end users and that it produces the impact that's needed within those communities. It also helps to identify any potential errors and risks that may have consequences. Ultimately designing in a way that's, again, comfortable and adoptable for end users and the organization. Also at Datakind, as I've probably you've heard already, I talk a lot about impact because we talk a lot about impact here at Datakind, but it's important to recognize that sometimes data science can't be a solution for everyone or everything. We try to take the questions that our partners bring up and identify which of those potential questions has the greatest likelihood of changing their systems. And within that, where can Datakind be of best help? It's important to recognize with humility that we are a tool in the toolbox, and what we offer is data science. And data science can be available to help observe the state of the world more effectively, as an example, or it could help reason through certain observations. It can even help inspire action. But there are some cases where a different tool is needed, and recognizing that it may not always be data science, and it's important to know that distinction. Also, ethics, privacy, and risk management should be prioritized from the start and monitored along the way of a project or a collaboration. We want to focus not just on what might happen if our project fails, but also what happens if our project succeeds. And this allows us to embed and have space to have those difficult conversations that may come up, such as if automation leads to a loss of jobs, or a tool that identifies vulnerable communities for positive outreach, but what happens if it falls in the wrong hands, etc. Those type of conversations. This is why I mentioned earlier, when we look for collaborative partners to work with, we look for those that have leadership that are willing to have these hard conversations in support of the communities that they serve. So with that said, that concludes a little bit about Datakind, but also things to think about as one is a part of a data for good type of project. And if you're curious to learn more about our work, you can certainly visit our website or follow us on social media. We do recruit volunteers, and oftentimes we share those opportunities through our social media channels, or you can sign up for our email updates by way of our website. So with that said, that concludes my presentation, and happy to answer any questions. Again, thank you all for joining me in today's presentation.
Awesome, Shanna. Thank you so much for it. It's very informative. I'm actually a huge fan of using data and helping out people as well. All the jobs I've been seeing with AI is all about, you know, doing some A/B testing, figuring out if this blue color is good or this red color is good. But, you know, I do want to move away from that, like any sort of business, and like try to actually apply it to the real world and try to get people to try to help people out.
Absolutely.
So just a quick question, like from my end, while we wait for others.
Yeah.
Like do people reach out to like Datakind saying, hey, I would love for you to partner up with us, or do you reach out to certain companies that are doing these humanitarian projects?
That's a great question. Oftentimes we're in a fortunate position where organizations hear about us through conversations like this today or other events. So oftentimes they reach out to us. They may come through our website as an example. And so recognizing, again, we're in a fortunate position where we do have quite a bit of organizations that reach out to us. So we do go through a process in which, like I mentioned in the Discover stage, where there's an opportunity to scope what that potential collaboration and project may look like. And in fact, one of the things I didn't mention, apologies, we do have a volunteer team. They're actually called the Scoping Squad that helps us in those conversations with the organizations. These are volunteers that are very comfortable in that ambiguity of connecting with an organization, finding out what their needs are, and potentially what the data science opportunity is. So yeah, we definitely have that outreach that occurs there.
Shannon, would you tell us a little bit about how you ended up where you are today, and just what your path has been?
Yeah, such I chuckle because it is not like an A to Z path as well. I sort of stumbled upon Datakind. So my background is actually in public health. I worked at the American Cancer Society for many, many years. And in that effort, we worked a lot with our grassroots volunteer community. That was actually a strength of the organization as we delved into areas such as research, advocacy for cancer-related issues, fundraising, patient services, etc. And so while I was at that organization, I actually had the opportunity to work on some initiatives specific to health equity. So recognizing that there are some very concerning disparities within cancer as it relates to mortality rates and survivorship, there was an opportunity to involve our volunteers in that effort. And one of the interesting things that I remember coming out of that is, as we partnered with community members, medical systems, et cetera, everyone kept saying, data, we need to figure out what to do with the data. So I kind of held on to that. And then just in being transparent, right? Because life happens, COVID happened, and I unfortunately was impacted through a layoff. So just keeping it real there, it happens, and it happened to me. And so this was an opportunity to kind of reevaluate and see where I wanted to pivot. And so I was very struck by the work of data science, how it can intersect to help public health, and do that through a volunteer network. So it really I was just fascinated and curious about the work that Datakind did, its volunteers, its global network, and really excited and happy to be here. It's really afforded an opportunity to also connect on expertise, right? Because full transparency, again, I am not a data scientist, but one of the value adds that I can bring to the table that often comes up in these projects is numbers also represent people and their lives. And so I could see the connection in terms of how to add context to that and how to help support those projects and potential solutions. So yeah, it was an interesting, like I didn't have it on my radar, but just through the curiosity and the interests I had, it really brought me to the organization.
Absolutely, that's amazing. I love that background, and we all need those vision people on top of just the data, because the data can tell us so much, but
absolutely,
got to be a bigger picture.
Absolutely. And it's just recognizing everybody has different expertise that they can offer, and bringing that together is what can help drive those project solutions, but also the sector-wide solutions.
Absolutely.
Great. Seeing a great comment. Thanks, Mel, for that.
Anybody else? Feel free to come off mute if you want to ask a question. Well, thank you so much for your time, and the presentation was amazing. I'm sure you will have a number of people going to Datakind to sign up to volunteer. I know I filled out an application a couple weeks ago. So I hope that helps your company as well as us, because we're all very excited.
Absolutely. And to your point, Hope, one of the things we're thinking through is how we can continue to offer additional volunteer opportunities, because I think one of the challenges is we have a certain number of projects at any given time. So that can sometimes limit how many volunteers that we can engage. So one of the things that I'm excited about is exploring how we can offer more opportunities on a frequent basis in ways that are low barrier for our volunteers to participate in.
Absolutely, that would be amazing, and I will stay tuned for that.
Yeah.
I think at this point we're gonna go to the Gather Town. I'm gonna put that link in here. I'm gonna share my screen here and give you all just a short little intro so that everybody can get to where it is. So when you go to Gather Town, you will have a setup where you get to set your character up, and there will be a little mini intro. And then when you join Gather Town, you should enter here. And you can go to if you hit X, it will pop up with the site here. Anywhere that you see it glowing like this, you have those options. You can also come in, and there are so many rooms to explore. But if you come in and go, the quickest way to get to the DJ room is to come in and go to this spot here and go to it. The other option is, even from that start area, you hit the calendar and go to the networking, and you can either teleport there here, or you can step on this box here. If you prefer to explore, there are plenty of rooms to explore. Just so you can see, I'm going to walk back here, and this is where the DJ room is in the whole setup. Each of these are private rooms if you want to come into a private room and have a chat. But as people join, you will be able, so there's TerraCore. If I go up to him and I turn my video on, then we will be able to chat, and he will be able to hear me on there. So everybody can leave the Zoom and go to Gather Town, and I expect it'll probably take people a couple minutes to get it set up and in, but you are welcome to come join us there. I'm not going to close the Zoom just yet, but if you want to head over, that would be terrific. Thank you, everyone.
Yep. And just to let you guys know, this is like the end of the New York chapter, but once again, the Global AI Festival is a whole month festival with people around the city, around the world, actually doing these AI presentations. So us being the first city in this festival, this might be a little, not that many people, but as the conferences go on throughout the month, we'll get more people involved, and it'll be a great opportunity to network with people all over the world. So, yep. So I'm in the DJ room. It's actually pretty cool. You hear some background music as well too. But yeah, if you guys have trouble, so this is open all month, so you could literally just exit out and then join back whenever there's another conference, and you'll have access to it.
I've also put the link in the chat for the City.AI festival page if you want to check out the other events coming up. Mm-hmm. And we welcome you to join any of those, or like he said, the room is open at all times for the next month. So if you want to go in there and see if anybody else is in there, there's also some games and stuff you can go in with a friend and play around.
So,
Thank you,
Thank you
everyone.
guys.
Thank you.
Thank you.
Thank you.
Welcome.